In this video I want to talk about the basic building blocks of any digital computer, more specifically logic gates. So logic gates are circuit components that enable us to perform logic functions. So here are some basic logic functions. We can have inversion, which is also shown as NOT. We can have AND, OR, NAND, NOR, and then later on we see how we can perform exclusive OR and exclusive NOR. So if we want to classify different logic gates, we can have logic gates with only single input. In this class we have the NOT gate and we have the buffer. We can have two input logic gates. The basic examples are AND, OR, XOR, NAND, NOR, and XNOR. And finally we can have multiple input gates that I will talk about them in a later slide. So let's just go over the two examples that I gave for single input logic gates. So first of all, let's just talk about the three different representations that we have for each one of these gates. So the first representation is a symbolic representation. As you can see, the symbol for the NOT gate is a triangle with a circle at the end. We have A as the input and we have Y as the output for this gate. So this is the symbolic representation of a NOT gate. The second representation is, you can say, a mathematical representation or a Boolean equation representation, in which the output is on the left side of the equal sign, and then we have some Boolean function on the right side. Here what we have is we have A, which is the input, and we have this bar which signifies the NOT operation or the complement operation that the NOT gate performs. And finally we have the third representation, which is generally called a truth table. So for a truth table, we have a table like this. So on the left side we list all the inputs to the gate, and on the right side we have all the outputs. So these three representations can be used for any logic circuit too. So it's not necessarily exclusive to single gates, but it is more general for all the different types of logic circuit that we can have. So we can have a symbolic representation, we can have a Boolean equation representation, and we can have a truth table representation. You will see later on how these things can be extended for more than one input and more than one output. So as I was saying, the truth table representation has the list of all the inputs in one side and the list of all the outputs on the other side. So for the inputs, since we are working with logic values, any of the inputs can either be 0 or 1 or false or true. So the truth table basically lists all the possible combinations of the input, and for each one of them determines the output value for that specific function. So as you can see on the left side of this figure, we have these three representations for the NOT gate, and on the right side we have the same representation, but this time it is for the buffer gate. So let's just go over the definition of the NOT gate. So the NOT gate or the complement gate has an output in which the output is the complement of input. So what does it mean? it means that if the input is 0, the output is going to be 1. If the input is 1, the output is going to be 0. Again, we are working with logic values, and logic values are either 0 or 1, or in another word, are either true or false, right? So when something is not 0, it is 1. Where something is not 1, it is 0. And that is basically the functionality of a NOT gate. Anytime its input is 0, its output is going to be 1, and anytime its input is 1, the output is going to be 0. So now let's just go through the 3 different representations of the buffer gate. So the symbolic representation of the buffer gate is a triangle without this circle at the end. And here again we have the input in the left, and we have the output to the right of the gate. As for the Boolean equation representation, we have y equal a. So that means that whatever the value of a is, y will be the same value. So based on this definition, we can complete this truth table. So for a value of a being 0, the value of y is also 0. For a value of a being 1, the value of y, or the output of the buffer gate, is also 1. So now you might ask, okay, it is understandable that we want to have a complement operation, right? But the buffer seems to not do anything at all, right? But in theory, you are right. But in reality, what happens is that when you have many gates, there are some other factors that need to be considered. For example, if you want to connect multiple outputs to a single input, right? There are some limitations in terms of the amount of current that that single output can provide, right? So if you don't have the buffer, your signals may suffer at the end. So that is one of the use cases of the buffer. Another use case is in practice, what happens is that different inputs experience different amount of delays to get to the output. So to make the amount of delays from the inputs to the outputs almost similar, sometimes it is necessary to introduce buffers in between the wires that we have, so we can introduce some more delay to some of the inputs, so all the delays is almost identical. We will go over these topics at a different lecture. So now that we have seen single input logic gates, let's just go to 2 input logic gates. So for this, again, as you can see, we have the 3 different representations: the symbolic representation, the Boolean equation representation, and the third one, the truth table representation. So let's just go over the AND gate and see what is the definition for the AND gate. So for the AND gate, the output is true if both of the inputs are true. So this is basically applies when you have more than 2 inputs, right? But for the 2 input AND gate, this is the one that that matters. Of course, considering all as well doesn't change the definition at all. So let me just repeat. The output of the AND gate is true only if all of its inputs are true. So here we have the symbol for the AND gate. We have the 2 inputs to the left, A and B, and we have the output to the right of the gate as Y. The Boolean equation representation of the AND gate is Y equals AB. So you can consider this as multiplication. Of course, it is different than the multiplication that we have seen in regular algebra. It is a logic multiplication, but it is a multiplication nonetheless. If you want to talk about in terms of programming, the output to this gate is true if both of these conditions are satisfied, right? So now, based on this, let's just fill out the truth table. So we said that the output of the AND gate is true if both or all of its inputs are true. So let's just go through it line by line and see for which one of these rows the output is going to be 1. For the first row, A is 0, B is 0. So since both of them are false, let me just erase this. Since both of these are false, the output is going to be false too, or 0. So that's why the output is going to be 0, because none of the conditions for the definition of the AND gate is satisfied. For the next row, A is 0, B is 1. So A is false, B is true. Again, since not both of them are 1, the output is going to be 0. A similar analogy can be made for the third row, in which A is 1, B is 0, which makes the output of the AND gate to be 0. But for the last row, as you can see, both A and B are 1 or true, which makes the output of the AND gate to be 1. You can plug these numbers into this equation too and come to the same conclusion. 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. And 1 multiplied by 1 is 1. So that was the definition of the AND gate. So now let's see what happens for the OR gate. So let's start with the definition. So the output of the OR gate is true if any of the inputs are true. So for AND gate, both of them had to be true, but for the OR gate, either of the inputs is true, the output is going to be true. So again, we have the symbolic representation. These are the inputs to the left, and we have y as the output to the right. So as for the Boolean equation representation, y equals a plus b. So again, this is the symbol for OR. So don't confuse it with the plus sign or the addition that we have in regular algebra. This is the definition or the symbol for OR in Boolean algebra. So now, based on this, let's just see what we can put in the truth table. So again, the definition of the OR says output is true if any of the inputs are true. So for the first one, A is 0, B is 0, which makes the output to be 0 because none of the inputs are true. On the other hand, for the second row, A is 0 or false, while B is 1 or true. And based on the definition, that makes the output to be 1. A similar analogy can be made for the third row, in which A is 1 and B is 0. So the output of the OR gate for the third row is going to be 1 as well. And finally, for the last row, we have both A and B to be true. And since the definition of the OR doesn't put any conditions on this, we can still consider this to be true, right? Because if both of the inputs are true, that means that any of them are true. So this is the result of having A and B both as 1, which makes the output to be 1 as well. So because of this, that there is no condition, OR is also called as inclusive OR as well, as opposed to what we will see later on for XOR or exclusive OR. So one thing that I want you to notice is that when we put or when we list the inputs in the truth table and we want to find all the possible combinations, as you can see, this generally follows the convention that we had for converting decimal numbers to binary numbers, right? So if you can pay attention, you see that if we consider this as a 2-bit binary number, its decimal equivalent is going to be 0. For the next row, it's going to be 1. For the next one, it's going to be 2. And for the last one, it's going to be 3, right? So even though the order of these rows in the truth table does not affect the output column of the truth table, but I highly recommend you to put them in order, because when you have more than 2 inputs, let's say when you have 3 inputs or when you have 4 inputs, all of a sudden you have 8 different rows for your truth table or 16 different rows for your truth table. So if you put them in order, it is very easy to verify if you included all of them in your truth table. But if you put them randomly, then it will be very hard to verify that, and you may end up with some rows that are repeated but at different locations in the truth table. So definitely remember how to count at least from 0, 0, 0, 0 to 1, 1, 1, 1. Of course, if you can count from 0, 0, 0, 0 to 1, 1, 1, 1, that means that you can count from 0, 0 to 1, 1. You can count from 0, 0, 0 to 1, 1, 1. And you can count even from 10 zeros to 10, 1, right? Because as long as you understand the concept and how it works, it is simply just counting numbers. So now we have seen 2 examples of single input logic gates, and we have seen 2 examples of 2 input logic gates. Based on those, we can define some other 2 input logic gates. So we have the NAND gate, which is the combination of an AND gate and a NOT gate. So if I want to separate these 2 gates, this is basically what a NAND gate is. So we have the AND gate here, and then we have the NOT gate. So combining these 2 creates the NAND gate. The same is true for the NOR gate too. So a NOR gate is the combination of an OR gate and a NOT gate. So this is an OR gate and this is a NOT gate. And based on those, their definition is mentioned here. So a NAND gate has an output that is the complement of an AND gate. So anytime the output of the AND gate is 0, the output of the NAND gate is going to be 1, and anytime the output of the AND gate is 1, the output of the NAND gate is 0. So let's just go through the different representations one by one. So again, we have the symbolic representation, we have the Boolean equation representation, and then finally we have the truth table representation. So for the NAND gate, we have A and B as the input. We have this circle that signifies this NOT operation, and then we have Y as the output. For the Boolean representation, we have AB bar, or A logic multiplication with B with a bar that signifies the NOT operation. So this bar represent this circle, represent this NOT gate. One thing that you should keep in mind, that AB bar is not equal to A bar B bar. So these are two different things. So this means that you first calculate the logic multiplication or the logic AND between A and B, and then you complement the output. This one says that you calculate the complement of A, calculate the complement of B, and then you AND the two together. So now, based on this, let's just fill out the truth table. So if you remember, for the AND gate, the output of the AND gate was 1 if both of the inputs or all of the inputs were 1. Otherwise, it was 0. So if I just quickly write the output of the AND gate here. So the output of the AND gate was 0 when both of the inputs were 0. It was 0 when one of the inputs were 0. And it was 1 if both of them were 1. For Y, as the output of the NAND gate, it is going to be the complement. So the output of the NAND gate is going to be 1 for the first 3 rows of the truth table, and it is going to be 0 for the last one. So to put it in words, the output of the NAND gate is 0 if both of the inputs are 1, otherwise it is 1. So now let's just see what happens for the NOR gate. Again, we have the symbolic representation with this circle that signifies this NOT gate. We have the Boolean equation representation, in which this bar represents the NOT gate again, and again this is different than A bar plus B bar, or A bar or B bar. Why? Because this means that you first calculate the OR of A and B, and then you complement the result. But this one says you calculate the complement of A, calculate the complement of B, and then you OR the results with each other. So now that we know this, let's just fill out the truth table. I just quickly write down the output for the OR gate here. So if you remember from the previous slide, the output of the OR gate was 1 if any of the inputs were 1. So that means that for the first row it was 0 because both of the inputs were 0, but for the other 3 rows the output was 1. So now that we have this, the output of the NOR gate here is shown as Y, is going to be 1 when both of the inputs are 1, and it's going to be 0 with when any of the inputs are 1. So this is how we can get from AND gate and OR gate to NAND gate and NOR gate. So now that we have seen this, let's just go introduce a little bit more complex 2-input logic gate, and that is XOR, or exclusive OR. So for the XOR gate, the output is true if either of the inputs but not both is true. So what does it mean? It means that it basically counts the number of inputs that are true. For the 2-input case, that means that only the output is going to be true only if one of the inputs is true, but not both of them. So this is the basic definition for the XOR. Again, the output is true if either of the inputs but not both is true. So the symbolic representation of the XOR gate is very similar to the OR gate, with the distinction of having this extra line. This extra line, we have it here. I don't know why I cannot draw this line, this line, this extra line. So in terms of symbolic representation, this is the only difference between the XOR and OR. When it comes to the Boolean equation representation, the symbol for XOR is a circle with a plus sign inside. So this signifies the definition or the distinction between XOR and simple OR. So now that we have seen this, let's just go through the truth table and see what are the outputs of the XOR gate given the different combinations of the input. Again, we know that the output of the XOR gate is true if either of the inputs but not both of them are true. So that means that when both of the inputs A and B are 0, the output is going to be 0. The same happens when both of them are 1, because that was another condition for the output to be 0, right? So when both of them are 0 or when both of them are 1, the output is 0. Otherwise, the output is going to be 1. Put it another way, you can say 2 input XOR is looking whether the 2 inputs are similar or not. If they are not similar, it makes the output 1, but if they are similar, it makes the output 0. So now that we have seen this, we can easily extend this definition to the XNOR, which again, similar to the NAND and NOR gate, it is one gate with a NOT at its output. So we have the XOR gate here, and then we have this NOT that in terms of the symbolic representation, this NOT is signified with this circle, and also in terms of the Boolean equation, it is signified with the bar on top of the equation. So again, don't confuse this with A bar XOR B bar. So this is A XOR B bar. So now based on this, we can fill out the truth table, and here we have the output for the XOR gate. So anytime that the output of the XOR is 0, the output of the XNOR is going to be 1, and anytime the output of the XOR is 1, the output of the XNOR is going to be 0. So we can simply just go line by line and find out what is the output of an XNOR gate. So for A and B being 0, the output of the XOR gate was 0, which makes the output of the XNOR gate to be 1. The same is true for the last row. When A and B were 1, the output of the XOR gate was 0, so that makes the output of XNOR to be 1. And for the second and third row, the output of the XNOR gate is going to be 0. So simply put, you can say 2 input XOR is looking for the inputs to be different. If the inputs are different, the output is going to be 1. On the other hand, for XNOR, the 2 input XNOR gate is looking for the inputs to be similar. If the inputs are similar, its output is 1. But if the inputs are not the same, the output is going to be 0. So now that we have this, we can generalize the definition for XOR and XNOR. And that's one of the differences between the XOR, XNOR, and the other gates that we have discussed. So for example, if you have an AND gate, so let's just say you have a 2-input AND gate, A, B, and you have the output, right? Let's just say you want to have an AND gate with 3 input, C. What you need to do is do like this, right? And still the definition for the output is going to be determined based on the same definition that you had for the 2-input gate. For the XNOR gate, that is a little bit different, and I highly suggest you try it on your own to see the difference. But the generalized definition for the XOR is that the output is true if an odd number of the inputs are true. So for the 2-input XOR gate, having an odd number of the inputs to be true is exactly similar as to say that the 2 inputs be different values, right? But if you have a 3-input XOR, or a 4-input, or a 5-input, or a 6-input XOR, that definition is not correct, is not accurate enough. So this generalized definition is more accurate. So again, the generalized XOR definition says that the output of the XOR gate is true if an odd number of inputs are true. Since the XNOR is the complement of XOR, we can have the generalized definition for XNOR like this. The output is true if an even number of inputs are true. So these are the two generalized definitions for XOR and XNOR. And again, I highly suggest you try to go from a 2-input XOR to a 3-input XOR and see how these definitions can be derived. So now that we have seen this, let's just go over some multiple input logic gates and see how they work. So here on the left we have a 3-input NOR gate. Again, like before, we have the inputs to the left and we have the output to the right. So this is the schematic representation of the 3-input NOR gate. Then we have the Boolean equation representation, in which we first calculate the OR of A and B and C, and then we calculate the complement. Again, this circle signifies this bar on top of the OR of A and B and C. And as for the definition, the 3-input OR gate has an output of 1 if any of the inputs is 1, and it has an output of 0 if all of the inputs are 0. So let me just write it like this. So the 3-input OR gate is going to be 0 if all of the inputs are 0, but it is 1 if any of the inputs are 1. So now based on this, we can easily calculate the output of a 3-input NOR gate. We know that the output of a 3-input NOR gate is the complement of the output of a 3-input OR gate. So that means that the output of the 3-input NOR gate is 1 if all the inputs are 0, and it is 0 otherwise. Once again, pay attention to the order of the rows in the truth table. So since we have 3 inputs, you can consider all the combinations here as a 3-bit binary number. So as you can see, if I convert these this 3-bit binary number into its decimal equivalent. This is going to be equal to 0 in base 10. This one is 1 in base 10. This one is 2 in base 10, 3 in base 10, 4 in base 10, 5 in base 10, 6 in base 10, and finally 7 in base 10. Again, if you have these all in order, it would be much easier to verify if you have included all the possible combinations. If you put them randomly, even though the truth table doesn't change, only you basically just switch different rows with each other, right? It would be much harder to detect if you have missed any of the combinations. Let's just take a look at another multi-input logic gate. So here we have the 3-input AND gate. We have again the inputs to the left and the output to the right. For the mathematical or like Boolean representation, we have A, B, C, or A and B and C. So if you remember the 2-input AND gate, the output was 1 if both or all of the inputs were 1. The same is true for the 3-input AND gate too. So unless all of the inputs are 1, which makes the output to be 1, if any of them are 0, the output is going to be 0. As I said before, you can consider this as an AND operation between these 3 inputs too. So 0 multiplied by 0 multiplied by 0 equals 0. Or for example, for this one, 1 multiplied by 0 multiplied by 1 is 0. Of course, you should know that AND and multiplication are completely different things, but for the purpose of this argument, you can consider them to be equal. So in this video, we have learned about the basic building blocks of any digital computer. We introduced logic gates. We went through a different classification of the logic gates: single input, double input, and multiple input logic gate. Of course, we didn't cover all the possible logic gates, but based on the definition that I just provided, you can derive any number of inputs or any number of different logic gates. So going from a 3-input AND gate to a 1000-input AND gate does not change its definition. The same is true, for example, for the XOR or XNOR, right? So we saw buffer and NOT gate, which were examples of single input logic gates. We saw AND and OR gate, which were example of 2 inputs and multiple input logic gates. We also saw a NAND and NOR gate, and also more importantly we saw XOR and XNOR gate, in which their definition was not as straightforward as AND and OR or NAND and NOR gate. They were a little bit more nuanced than that. So definitely try to memorize the definitions for XOR and XNOR gate, because they can be very useful in some applications.